How are we doing today?
Woo!
Are we enjoying
Better
Freaknik?
now that you're here, church.
Better now that I'm here. Oh, y'all are so kind. So the first Freaknik, I don't remember my first Freaknik, but the first Freaknik I spoke at was probably 14, and then I spoke at one 3 years ago. So this is my third time to speak at Freaknik. A little bit about myself. My name is Dr. James Church. I am an associate professor at Austin Peay State University. I earned my PhD a few years ago. I really love to teach. I really love to explore new technologies and then try to put them in front of people who might be able to use them and extend them beyond whatever small little thing I can create in a short amount of time. That is where I'm coming from as an educator. So we're going to start off first with the demonstration. This is a talk about machine learning and neural networks, and I wanted to do a live neural network demonstration while we're here. So right here I've got some poker data, and let's talk about poker for a little bit. If you're playing 5-card stud, that means you get a you're dealt. Let's see where your 5-card draw. There we go. That's more like it. And how many different possible hands are there in 5-card draw? First off, how many cards are in a deck? 52. And I've already lost signal. There we go. Let's bring it back. This adapter is finicky. There we go. I just have to be very careful and not touch it and not kick this wire. So if I were to, let's start up Python, and so if there's 52 cards in the deck, there you go. I draw you 1 card, and then I draw you a 2nd card, and then I draw you a 3rd card. I draw you a 4th card, and then I draw you a 5th card. There are 311 million possible poker hands that you should be that is possible to be dealt in a game of poker. It's a very large variety. And what I have here, and I pulled this data set off the University of Michigan UC machine learning data set repository. What this is a poker hand database. So let's just look at the poker hand training. Poker hand training data set. What you're going to see on the screen is a whole bunch of rows, but there are 11 numbers across the row. So what we have here is a 1 and a 10. Now that represents, the first number is a 1, that represents a suit, and the 10 represents the card was a 10 value. Then we have a 1 and an 11, a 1 and a 13, a 1 and a 12, and a 1 and a 1. I'm sorry, a 12, let's see, a 1 and a 12, and then a 1 and a 1, and then a 9. And the 9 on the end, that's the 11th number, that represents the hand that was dealt. All right, so if I look at pokerhand.names, this is another file that comes with the data set. Always look up the metadata that comes with your particular data set. We're going to scroll down a little bit. We actually get to see what these attributes are. Attribute 1, hearts, spades, diamonds, clubs. And then attribute 2, ace, all the way to king. If I scroll down to the bottom, you can see that this alternates suit, number, suit, number, suit, number, all the way down until we get to number 11, where we get the class of the poker hands, and we see that there are 10 visible classes of poker hands. Nothing in the hand, not recognized as a poker hand. What was the one that we put up on the screen here, that first line, that was a 9. If I go back to it real quick, that first line, you can see it was a 9 on the end. So if you just pick out those numbers, and those of you who play a little bit of poker, that would be a royal flush. And sure enough, number 9 is indeed our royal flush category. So the idea behind machine learning neural networks is that we are going to create a whole bunch of inputs and a whole bunch of outputs, and then we're going to train a model. And whenever we first start off with the model is just going to be a bunch of random numbers that don't really make a whole lot of sense. and then we're going to pass our inputs through the model, which starts off initially random, and passing through the inputs, and then try to retrain the model based on this. So let's bring up my code. And just the mere fact of typing is causing this wire to shake, so I'm going to have to type a little bit softer. So here is our a little short Python program. It's only 39 lines. We're using TensorFlow and NumPy. And I've got, we're going to read in the files. I do a lot of data massaging. You can see where I'm alternating the lines here. So I get everything on a scale of 0 to 1. We cast that to 32-bit floats. It turns out that a 32-bit float is, for our purposes, just as good as a 64-bit float, and we work a little bit faster. So a nice little perk of converting everything to 32-bit floats. And then we're going to perform we're going to build the neural network model. We're going to have a 20-node hidden layer. We're going to have a dropout of 0.2. Every time we pass through a layer, we're going to drop 0.2% of our results. And then we are going to pass it on to our output layer, which is going to be the final categorization. And after we build the model, we compile it. I'm using the sparse categorical cross-entropy loss model, and we are looking for accuracy. We're going to fit, and then we are going to evaluate based on a test set. Now, here's the thing I may not have told you. TensorFlow is a really hard piece of software to install, and so I don't have it installed on my laptop, but I do have Docker. So we're going to get Docker going and then use that. So let's get Docker going. So there we go. Let's get Docker going. Docker images. The best way to use TensorFlow is to not even bother installing it on your computer. Just get the Docker image. Let's go ahead and pull. I've already got it pulled down. Let's do Docker run IT. This is going to be TensorFlow latest PY3, and then we are going to bash. There we go. This runs this is a container running on top of my host operating system. We now need to put our files over. So whenever I just type ls-al, you can see that I've got, it's just the standard root file system. There's nothing on it. This is a clean installation. Let's go ahead and move our files over. So we'll do Docker copy. We'll just do everything over to, let's see here. What are my Docker PSs? All right. My Docker instance is named Intelligent Allen. There we go. So let's do Docker CP, everything over to Intelligent Allen. We'll just drop it into the root folder. I'm going to swap back over to my TensorFlow environment. Now if I hit ls-al again, I now get my script appearing in the Docker container, which you saw, and now you can't see it anymore because I nudged the wire. Feel free to stop me if you have any questions. I do tend to work more in an environment where I have lots of students writing every word down I say on paper, and so having you just stare back at me is kind of I like the interaction between what I do in front of the classroom and what the students do.
So I had a question about the dense. You started with 20, then you did the you dropped 2%, and
yes.
then you went to 11. What were the choices for 20 and 11?
I just picked them arbitrarily.
Okay.
I don't have VI because it's a Docker container.
Well, you
and
cat it. Cat the file.
I can cat the file.
That's some commands that you would run. So,
Yeah.
which Docker?
Yeah.
Which Docker? Oh, go ahead. What was that?
TensorFlow /
Oh yeah, I was using the Python 3 implementation of TensorFlow. So I'm using the tag latest-py3. So there we go. The reason why I went with 20 and 11, I wanted to make sure that there were just more nodes in my layers than there were actual output categories, just to provide a little bit of
A rich soup.
Hmm?
A rich soup.
A rich soup, a good soup. All right, so let's start up the test. So we'll do, there we go, Python 3, evaluate. Now I'm going to be running 10,000 epochs of this particular neural network, and that may take the entire presentation. So what we're going to do is we're just going to start it off, and it's going to go through the code. Notice the code wasn't really that long. That's one of the things I appreciate about TensorFlow. As soon as it takes a long time just to load the files. And now we're getting it up, and now you can see we're going through the epochs. And there's my 10,000 right there. We're on 12 of 10,000. And you can watch over here the accuracy slowly creep up as we go through the presentation. And hopefully that accuracy will get pretty high. Right now we're at about 48% accuracy after just a few epochs. We're going to just let that cake bake, and we're going to come back to it. How about that? Hey, let's talk about neural networks. All right. So I titled the talk, Rigging the Game in Your Favor. Machine learning is now accessible to everyone. So as you saw, all you have to do is get Docker installed on your system, find the TensorFlow container that has TensorFlow already installed, and then write a little bit of code, and now we can start doing machine learning right off the bat. So here we go. Machine learning in the news. I wanted to go just a brief overview of what is machine learning and machine learning in the news. We've been seeing lots of instances of, and I kicked the wire again. We've seen lots of instances of machine learning being applied to games, most notably chess and Go. So we now have AlphaGo, which has pretty much taken over some of our best worldwide Go players that will allow you to, that currently play Go. Good, you've seen that one. Ooh. I'm so sorry. We now have MIT Poker. There's an AI poker bot that whips the pros. All right, that is, we're now at the point where AI has taken over the game Heartstone. Heartstone is now no longer it's still a fun game to play, but now it's to the point where computers can play it no problem at all. As we've seen in the news lately, we've got the Microsoft and Amazon are both trying to market their own machine learning based person identification systems to law enforcement. And of course the ACLU is all over this, wanting to have some sort of civil liberties applied to machine learning and facial recognition. And just a few days ago, IBM jumped into the conversation, not with their own product, but just to comment on what other major companies are doing, saying, hey, let's not outlaw this technology, let's heavily regulate this technology. Any comment on what would be better for facial recognition software used by law enforcement? Would you rather have it just outlawed altogether, or would you rather have it regulated?
Obviously, the government's not going to screw us over.
No.
Right.
But IBM is of the position, let's go ahead and regulate it. Okay. So our goals with machine learning is we're trying to create simple prediction machines, but without the tedious task of handling every single circumstance. How many different poker hands are there that we had? 300 million plus. There's a lot. Could we write code that handles all 300 million possible combinations? We could. I could probably sit down and go through all the different possible hands. We can sort them and say check the suits for the flushes and all that. And then I would have to go through the process of testing all of that. Based on a chessboard layout, what will my opponent do next? That would be a great machine learning project. Based on a poker hand, what should I raise or fold to maximize my chances of a win? Based on a crowd, are there any people with outstanding warrants? There's lots of interesting applications of these machine learning projects. One thing I would like to mention is the game of chess. The game of chess when it comes to AI has changed dramatically over the last 20 years. before, whenever we had the classic games between, in the 90s, Garry Kasparov and Deep Blue, those were done with mostly tree-based searches in which a programmer with a computer would manually program all the different possible moves that every possible piece on a chessboard could make. So what are the moves that a queen can make? It can move one space in any direction. So a programmer would sit down and say, oh, a queen can move one space in any direction. Nowadays, that's no longer done with chess AIs. What they'll do is they'll just dump a huge number of chess games into a machine learning framework, much like the one I'm using here with TensorFlow, and the game will automatically learn what is a legal or an illegal move. If it's a legal move, it'll find it in the database. If it's an illegal move, it won't find it in the database. So chess AIs nowadays start from having no knowledge of what the pieces do, and then can work up from there to be as strong as professional chess players. All right, which is something that I find fascinating behind how just the state of artificial intelligence in which it's moving. So what I'm trying to say is, don't try to solve the problem yourself. Let the machine solve the problem. I've got this wonderful laptop here. It's going to tell me what are chess hands, not chess hands. While I'm letting my program bake, it's going to tell me what poker hands are based on how well based on the giant database that I've provided.
Is the device getting noticeably warmer?
No, not right now. I do have it plugged in, because if I didn't have it plugged in, my laptop would probably die during the presentation. It is a very computationally intensive process, and I don't have the greatest laptop in the world, so that's why this is taking this is going to take a long amount of time. But that's the idea in neural networks. It's through a lot of repetition. It's like teaching a small child. How do you teach a small child? With a lot of repetition. All right, so here's the basic flow chart, and it's really simple for machine learning. You have a question, you think on it, and you get an answer. All right, so more importantly, from the perspective of a software developer, we might flip that on its head and say something along the lines of, I have a set of inputs, now process it, and then let's look at the outputs. But the inputs and the outputs are what I have to start with. What I want is to give the program the inputs and the outputs, and its processing, it figures out how to translate inputs to outputs. So there you go. Let's go through a real simple example of this, just us together. Imagine that I give you a task for everyone in the room. I say, how many, let's write a program that converts kilometers to miles. All right, so if I want to convert kilometers to miles, what I'm going to do is I'm going to say, we're going to give it an input and an output, and then I go, kilometers to miles is 0.5. And all right, so is 25 kilometers equal to, I'm sorry, is 50 kilometers equals to 25 miles? No. What we'll do after that is we'll record the error term. So the correct answer in this case, if you don't have that ability, just do the math in your head, it's 31.06 miles is equal to 50 kilometers. So the answer we gave was 25 miles. Obviously that's an error of 0.6 miles. So we have 0.6 miles, and we know that we probably need to adjust that term and make it, or should we make the term larger, or we should make this middle term smaller? We gave it 25 miles, the real answer is 31.6. I need to make my term smaller. I need to make this 0.5 larger. Yeah, we're going to make that larger. Okay. And what we do whenever we have neural networks is we just start with random numbers. And so whenever the program runs through the neural network, what's going to happen is it's going to get a lot of things wrong. And that's okay, because we're learning. This is machine learning. So we're going to get it wrong, and we're going to get it wrong a lot. And that's part of the education process, is getting it wrong a lot and then getting back on track. All right, so if I bump this up to 0.7, I get 35 miles. which is closer. Did I overshoot my correct answer of 31.06? I did. So what do I need to do now? I've got my term here. I need to make it smaller. I know that I don't need to make it smaller than 0.5, but I need to make it somewhat smaller. Okay, so let's split the difference. I'm going to go 0.6. All right, so there's my 0.6 term. 50 times 0.6, I get 30 miles. Great. I now have 31.06 miles, an error of 1.06 miles. I'm getting closer to my goal. All right. So as you can see, we keep iterating through the process in order to keep improving our accuracy. This is what's known in a neural network as a perceptron. And a perceptron is just a single node in which we multiply an input by a random value, and then we get an output. And this is known as a perceptron. I like to name my perceptrons Percy. Percy the perceptron. And you can do quite a bit with Percy the perceptron. It turns out that most of the machine learning problems that we deal with really only require one little perceptron, and that does quite a bit. We call this a linear solution. You take Percy the perceptron, you multiply by a number, you add a constant, and usually you can map one thing into another really easily with a small error term. This is also known in machine learning as linear regression, which are usually taught in an introductory statistics course. But here we're doing it in a roundabout way in which we just have one node. Okay. So to recap, usually when we think about programming, we think about inputs and algorithms. So if I want to translate kilometers to miles, what I'll have to do is I'll go look up on a chart what is the factor that translates kilometers to miles, and then I'll write a little program, multiply this times 0.61, and then I'll get a response. But with machine learning, we're flipping that on its head. We have large amounts of inputs and large amounts of outputs, and we let the computer create the algorithm for us. Programmers, if you were worried about your jobs, you can now be worried about your jobs. So there we go. Well, soon, we'll explore the neural networks will be expanded towards more areas, things that we haven't thought of yet, and I do think that this is an exciting area. So we use the error term produced by our model in order to help improve the model. So it's a continuous cycle of checking in. Hey, checking in with our model. Hey, let's check in with our model. Let's see how we're doing here. We're at about 54% accuracy. How we're doing here. We got 1,400 of our 10,000 epoch iterations that we're doing. Good. Hopefully, I will get. Go ahead.
So to recap, what's going on the screen right now is that it's looking at all of those poker hands and trying to come up with that better thinking value.
Yeah, that better thinking value. Oh, we're trying to take a list of 10 values and map it to one value. But every set of 10 values is different, and they all map to one of 0 to 9. And so we're just constantly going back and forth, look at this 10 values, map it to one value, and we're trying to do this without having to manually write the code. Okay, if I have these 5 cards, it's going to be a royal flush, and if I have these 5 cards, it's going to be a straight.
So is it building a net or building a tree?
We're building a network. This is a network.
So is it just kind of doing an evolutionary process of just like randomly mutating all of those transformations and throwing away the ones that don't get closer to the right outputs?
Well, what it's doing, it's called a back propagation, where it will, after it figures out that it got an error term, it will go back and tweak each of those random values by just a little bit, by just a tiny amount, in the direction that will favor whatever the last run that just failed, in order to push it more towards the correct answer. So
does it take more time as it builds more epochs?
yes, it takes more time.
Okay.
There we go. We're watching it work. We're now at 1,500. We'll see how far this gets along while I am giving my talk. Okay. So there we go. This is a general overall flowchart of machine learning. This is not particularly tied to neural networks. I just wanted to have a slide in here that was geared towards the broader scope of machine learning.
So if in machine learning, if there's bias in the data sets themselves, so it's not going to happen in your kilometers to miles example. But
No.
for example, if you're using it to narrow candidates to be hired, and what you're looking at has bias in it, the machine will learn the bias, right?
Yeah, the machine will learn the bias. That's called
So-
overfitting.
Okay.
Yes.
So I was reading about that actually this morning, and it was an article that said that what you should do in that example is you should have audits of the outcomes in the process by people who didn't write the program in the first place.
Oh, a domain expert. Yes, yes. So one of the things that I'm going to hope, if this finishes by the time I stop, I think I probably should have set this at about 4,000 or 5,000 instead of 10,000. But I'll go back over to, let's go back over to my data set. So you'll notice here that I have 3 files up on the screen. I've got the names, which I showed you. It's just a description of all the poker hands. I've got the training set. That's really what you're seeing the program go through as the model is learning. And then I have a testing set, which I loaded in, but at that stage that you're seeing up on the screen, the testing phase hasn't even occurred. So one of the nice things about TensorFlow is that you can do that analysis between an outside expert and machine learning as long as you've separated out your data into a training set and a test set that you can explore, that you can evaluate your model. So if we take a look at that test set, you'll notice that it's pretty much the same data. Well, it's pretty much the same file format. It's just different data. Well, we got rows of 11 numbers each. Okay. So we have rows of 11 numbers each, and then what the program is training on is the first file that I showed you, and what it's going to test on later is the second file. And really the true judge of a model, in the case of biases, obviously, or in the case of, in the case of biases or overfitting or any number of such problems, the real test will be whenever we examine something that has never touched our model at all. Now, what I've noticed a lot of what a lot of people do whenever they're working on neural networks is they'll work with the training set, they'll tweak the data, they'll get a result, and then they'll run back over to their test set, and they'll evaluate it, and they'll get a response. And they'll go, I don't like that response. And then they'll run back over to their training set, tweak the code a little bit more, run the analysis again, evaluate on the test set, and then go, I like that response better. Can you see a problem with this approach where I'm just going back and forth between my training and my test set? Basically, I'm using my test set to train my training set. And then I'm implicitly crafting my code to pick up all of the biases that exist not only in my training set, but in my test set as well. So one of the things that I recommend to students just starting off in machine learning is get a whole lot of data and slice off just a tiny chunk of cheese and make that your training set, and then slice off just another tiny, even smaller chunk of cheese and make that your test set, and then test and then train, and then as soon as you're done with that evaluation, merge that testing data into your training data because it's no longer any good. Always keep your test data fresh with new test data. Let's go back to the slides. Just an overview of some of the things that we can look for whenever we're doing machine learning. Supervised learning, reinforcement learning, unsupervised learning. There we go. These are different types. And then, as you were mentioning, these are some of the problems of learning. We get a lot of noise in the data, bad data results based on inaccurate data. Now, the data set that I'm working with here, the poker hand database, that's perfect data. There's not going to be any inaccuracies in there. So hopefully what I'll do is I'll get a very nice high accuracy whenever this is done. But not every data set is perfect. Imagine that you've got a face that resembles someone who does have an outstanding warrant. Well, then that is an example of something that, well, could potentially throw off a model. Specific features of training are learned. For example, what if it just so happens that you have a data set of criminals, and it turns out all of your criminals are wearing glasses, and none of your free people are wearing glasses, and then, oh, what do you know? You now put on glasses. Well then, oh, that's the sign the machine looks for. Irrelevant features are learned. Learned concepts cannot be generalized because, as we said, this is just a bunch of random numbers inside of a model. You can't really go back and inspect your model and see what is being generalized by the model, because it is just an array of random numbers. And noise is often learned, especially if you have a very noisy data set. One of the questions I like to ask in machine learning is a hot dog a sandwich?
Yes.
Is a hot dog a sandwich?
Yes.
Anyone would like to disagree?
Yes.
No.
No? Are hot dog sandwiches? There we go. Are taco sandwiches?
No, they're hot dogs.
It depends.
One of the things you said is that you can't go back to see the decision that was made
Mhm.
and why it made that decision, because it's just a bunch of data. But isn't like over in the EU, they're passing laws to put that into AI so that you have to be able to say why it made this decision?
Why is this one node in my neural network 0.4, and why did that flag this one decision of hot dogs being justified as sandwiches? Basically, I would have to point to a node or a collection of nodes and say, these nodes all landed on this particular range of values, therefore hot dogs are sandwiches.
Need a larger data set.
Yes. So another thing that I like to remind students is the simplest concept that classifies all of the examples correctly is likely the best one. So try to avoid complex models. Try to go for simplistic models that handle your data set in a nice, succinct manner. All right. Thank you so much for your participation. I mean, I enjoy the back and forth. So let's talk a little bit about the history of neural networks. And so this is a diagram of the first sketch of the neurons of a brain from 1899. This was one of the first brain surgeons. And what they realized was that as decisions are being made in your head, well then there's these little pulses that go through the neurons in your brain. And so as you're thinking through problems, different neurons will get strengthened based on whatever your skill sets are. Not everyone is a chess master, but if you looked at the brain of a chess master, you would probably see a range of neurons that accentuated more towards chess, because those neurons had just been trained from years of practice. So there we have the different parts of the neurons. And then here we have the computer model of the neurons. So here we have a set of inputs. Here I have x1, x2, x3. You can think of this as a problem with 3 inputs. And here we have 3 edges towards a node that has 3 weights. We'll call them W1, W2, W3. And all we're going to do is multiply them together, multiply x1 and w1, x2 and w2, x3 and w3, and then we're going to add them all together. And then we're going to, once we get a score, that score should be out of a range of 0 to 1, and then we're going to test to see if it's greater than a threshold t. And if it turns out that score is greater than a threshold t, then we're going to say 0 or 1, and we're going to have a result of 0 or 1. And it could be right and it could be wrong. All right, but that's the basic mathematics right there behind how neural networks work. And what we're doing is just evaluating this on a large scale with dozens and sometimes even hundreds of neurons. So the original neuron, I mentioned my favorite little neuron, Percy the Perceptron. Percy the Perceptron was first discovered by Frank Rosenblatt in 1957, who created a real simple two-layer network called, that he just referred to as the input layer and the output layer, and was able to just using just two layers, one for inputs, one for outputs, we create models and functions for classifications. All right. And then we're going to have a little bit of history since then. Marvin Minsky, the famous artificial intelligence scientist at MIT, did a study on neural networks and found out that pretty much if you just did linear regression on the vast majority of your problems, you didn't need neural networks. And that was its decision. And then for the next, say, 10 years or so, no one really touched neural networks. There was a declining interest in neural networks after that point. But at this point, in the 1980s, research was renewed, and now we have multi-layered networks. We have networks with 3 layers now. In addition to the input and the output layer, we have a hidden layer. And if we go back to my code, what I like to do is I like to make sure that all of my networks have a hidden layer. So here, the input layer is always set by whatever problem you're working with. I'm going to have my hidden, the input layer comes in, that's tacked on to every model. We're going to have a hidden layer. This is known as the dropout, which after every pass through the model, they're going to drop some of the results of the hidden layer. That's an attempt to remove a little bit of bias from the neural network. And then we're going to pass it on to the output layer, in which we get the output of my results. But there's my hidden layer, and then there's my output layer. So TensorFlow handles input layers and output layers just fine. But a lot of research was put into this time in the 1980s, and it was just decided that you only needed 3 layers and you could solve any problem. So that's pretty much where it stood. In fact, whenever I was in grad school, I remember having professors tell me, you don't need more than 3 layers. 3 layers is the best we'll ever need. Input, hidden, output. Great. Now, within the last, say, 5 or 6 years or so, we now have convolution neural networks where we say, all right, why limit ourselves to 3 layers? We can have a dozen layers. We can now work with audio and video and add hidden, where different parts of the audio and video can now be mapped to different layers within a convolution neural network.
We can play the record backward.
No.
Oh, sorry.
So here is an example of a diagram of a fully connected neural network. So here we have our input layer represented with eyes. Here, we imagine that we have 5 inputs, and so the I0 doesn't count as an input. It's known as the bias. It's an attempt to add a little randomness to our layers just in case something sneaks in. Here we have our hidden layers. Notice I've got 4 hidden layers, and then I'll have 2 output layers in case I'm working on a 2 classification problem. So input layers and output layers have clear meanings. The hidden layer, the one that I keep mentioning, is really where the mysteries of the neural network happen. Right now, it's really just a summation formula where you multiply each of these arrows. Each of these arrows will have a number associated with it. And then, of course, your inputs all have numbers. And then you multiply the input by the weight, and then you add them all up. And then that number will get dropped off into one of these hidden layers. And then you do it again for the next pass through, from the hidden layers to the output layer. At some point, go ahead.
Trying to understand what the training data would look like with that diagram. Would it just be 5 columns of input data and then 2 columns of output data?
That's exactly right.
Okay.
It's a 5-column input, 2-column output. 5-column input, 2-column output. All right. And this is what's known as a fully connected layer, because every single node is connected to every single node in the next layer. So there we go. And then, as you can see, every node has an arrow spanning to the next layer.
Would it be
Alright.
6 instead of 5? Yeah.
6.
Well, I mean, you said there's 5 columns and.
Yeah, 5 columns. So 1, 2, 3, 4, 5, and then 2 output. And we just kind of leave the 6th one, I0. That just kind of gets set with a random number and doesn't really get touched. It's known as the bias. So it introduces its own little bias to the network just to prevent, and suppose you don't have enough data. There's a little bit still addition randomness in addition to the data that you're supplying.
It's depending on the jar if you don't have enough change.
Yeah, jar you don't have enough change. There we go.
Could you simulate a convolutional network by just disconnecting some of the input nodes on the network?
Oh yes, just have more hidden layers.
No. Have one hidden layer, but just have it wider.
Just have it wider? Oh, okay.
I'm asking that.
I have never experimented with that. I'm sure we could. I have never experimented with that. Rather than have just layers, so this is a 3-layer, have, I guess you could say, parallel layers.
Just so part of the if you add too many nodes in the hidden layer,
Mhm.
then it becomes a lot easier to for the net to memorize your training set.
Yes.
But if you break that up, then you could simulate a convolutional network.
Convolution neural network. Okay.
I'm asking. I'm guessing.
I believe you at this point.
I'm not making any assertions. I'm
Okay.
because I don't know enough about convolutional networks.
I don't know enough about convolutional neural networks too. I've never explored them. I've only dealt with the traditional hidden layer approach.
Okay.
So it looks like the hidden layers don't talk to each other, is that true?
That's true. You'll notice that there are no arrows connecting a hidden layer to another hidden layer. They are all independent of each other.
Do you have any tips or rules around picking the size of your hidden layer?
Smaller is better.
Smaller is better.
Why not a hidden? Why not a hidden size of 1 then?
So there we go. That's Percy the Perceptron. So Percy the Perceptron, you have a hidden layer size of 1. You can that's basically doing linear regression on your data. So if you think of this as maybe a parametric formalization, having 4 hidden layer nodes, that means I have a 4-node a 4-term parameter equation that I'm trying to solve. It's not the same, but I think of it as a 4-term parametric equation. The more terms you add to your equation, the more of a complex regression that you're going to have to solve. Whereas the more nodes you add to a neural network, the more training that you're going to have to do. All right, and as we've talked, so we give it the training data, we give it a number of layers in the neural network and the number of nodes per layer. What we then do is we pass the data in and we let it bake, and this takes a long time. And we just let it sit there and we wait. There have been stories of neural networks taking months and months to train. And so it's a slow process. And one of the great things about the TensorFlow library is that it's pre-built with code in order to take advantage of GPU processors. So if you have a GPU processor that and a version of Linux that can take advantage of your GPU processor, once you get TensorFlow installed, in fact, the Docker version of TensorFlow automatically has the GPU hooks already enabled, and then you can take advantage of your GPU processor and create faster models.
Are your students allowed to use Titans?
And my students allowed to use what?
Titan GPUs.
Yes, they can.
That computational intensity is mostly on the training, though.
Yeah, it's on the
right?
training.
Yeah. So once you actually have the model, it's fairly cheap computationally to run it.
Oh yeah, it's the model itself is really small. You can save it, and it's just a few bytes really. And then you take an input, you pass it through the bytes, it's a real simple equation, and then you get your output. It takes fraction of a fraction of a fraction of a second. But it's the training that happens is where the cost is. All right. So I did mention that we like to put in thresholds. I like to put in a threshold of 0.5 on my nodes, but you can tweak your neural network as desired. If a result on an output node is greater than 0.5, we say that's a 1, and if it's less than 0.5, we say that's a 0. And then we do the back propagation, in which we fiddle with the hidden node in order to improve the results of that hidden node. And what that means is simply tweaking the little bits of the hidden node in order to bias it more towards the solution of the test that I just ran. So rule of thumb, less weights than your training examples. So there we go. When to terminate back propagation, you just run out of data. You have a stop set, or you start working on your test set. Okay. Let's talk about, while I'm finishing up here, we're reaching the end of our talk. The disadvantages of neural networks: it's not able really to mimic the brain. I mean, this was all designed with the influence of, yeah, we're mimicking the brain. And then as we've learned more about brain science in the last several decades, no, we're not mimicking the brain. But we have explored a very interesting portion of computer science. Training is very time consuming. Scaling is difficult because new training is necessary even if the inputs are increased. And the value of the weights in the hidden layer often don't have a clear meaning. You brought up that point midway through the talk where you asked about the European Union requiring that we justify the meaning of our hidden layer. Obviously, the values of that hidden layer don't really have a clear meaning.
The issue, though, is if you have AIs making decisions like, do you get this bank loan or not?
Yep.
Why didn't you get the bank loan?
Yep.
If it's a person, they can answer you.
Mm-hmm.
So if you're, so say you've trained a model.
Yep.
And it's, a few months later and you have a bunch of new training data. Does that training, so you want to add in some new data into your existing training set and retrain the model, does that take the same amount of time, or are you able to start from your current model and then just train with your new data?
You could start with your current model. I'm not sure how wise that would be. I would start over.
Okay. So you can, but it's
You
not a
can.
good idea.
I would start over with a fresh set.
Why is that?
Good question. I just, part of me says I wouldn't do it. I would start fresh, just to make sure that nothing was missed. Anyway, it's a good question. I don't.
So would you take the original training data and add the new training data and then retrain the larger set?
I would take my new training data. I would incorporate the test data from any previous test. I would incorporate the new training data, and then I would go out and find new testing data. Because every time you run through one of these tests, you have to find new testing data.
So there's some assumptions there. One of the assumptions is that the new data is going to have different input size, and so that's going to change the architecture
Oh, yes.
of the array,
If-
of the thing. So the weights aren't going to be able to be mapped
Mapped
directly
properly.
to the new
If you're adding new variables, well, then you have to start over from scratch.
Yeah.
But if you're adding just new instances where you're trying to solve the same problem as before, then yeah, you can start fresh from new.
Well, I mean, you wouldn't even necessarily need to retrain.
Yeah, we're going to train anything. Yeah, you can just.
You're just using depending on, it might give incorrect results.
Okay. And then we fiddle with the bits further. Yes.
Someone asked earlier, do you have lots of individuals and you're evolving them? And the answer is no. I've got one individual and I'm iteratively improving it. I understood that right, correct?
Right.
Okay. So when we do the genetic algorithms and we have hundreds or thousands of individuals And we're not only picking the more fit ones as we evolve them, we're also mating them.
Yeah.
They say once you get to an acceptable solution, don't stop there, but keep going longer. And what you end up with is a more evolutionarily fit individual, which is better able to understand a change of environment, which you might consider an addition of more tests to be a change of environment. So I'm used to this rather than having one individual. If they asked you, should we start from scratch or start with an existing one, which is pretty good, I mean, my answer would be a bunch of these and a bunch of these and let them mate.
Let them mate. Genetic algorithms are its own branch.
Okay.
And that's a real interesting topic in and of itself.
But it looks like it could mix with this kind of iterative improvement as well.
Oh, where you take two nodes and possibly combine them?
Yeah, or you start lots of these these neural networks, and then you pick the better ones, and
oh, okay, I see.
Which is kind of what you do with
you have two competing models.
Yeah.
That arrange on slightly different results, and then you combine those two models.
Yeah, the first half of this and the second half of that one. How would that do?
We have 7 billion models. That must be more generative adversarial networks. Maybe.
Yeah. I don't know. I'm just trying to fit this into what I've done before.
Okay. Awesome.
Okay.
So here's my guidelines on when not to use a neural network. Can you flowchart your algorithm pretty easily? If it's a really simple flowchart, then a neural network is probably overkill. Do you want to identify solutions not related to your inputs? Use genetic algorithms. So there you go. Genetic algorithms are great for exploring areas way beyond your inputs. So there we go. Can you generate all possible inputs with a little bit of code? In other words, if you have a really small problem space like tic-tac-toe, you probably don't need a neural network. You could probably map out everything in tic-tac-toe in a little bit of, probably an afternoon. Does the problem involve discrete mathematics? Just use discrete mathematics. And does the problem involve extremely precise measurements for output? Figure out a formula. And for instance, while it was fun to go through the exercise of converting kilometers to miles, what would probably work better? A neural network or just knowing the formula? But there you go. Neural networks are great for solving complex problems in which there is a classification aspect to it. So you've got a very complex problem, but you think you have an okay-ish understanding of the inputs, now's the time to use a neural network. You've got an extremely large problem, and you aren't sure how inputs map to outputs, and you're willing to accept fuzziness of the output. And my favorite question, is a hot dog a sandwich? So there's
no, because you wouldn't cut it.
You wouldn't cut it. Oh, exactly. There we go. We have determined the extra parameter. Was it cut?
Yeah.
Now I have to rerun my neural network from scratch. All right.
Can you say that one more time? What you just said.
Oh, so what defines a sandwich? All right, you got bread, you've got, and then you've got bread with a type of meat, maybe it's not meat, maybe it's peanut butter and jelly, and then he asked, do you cut it? And so there we go, we've added a new parameter in what defines a sandwich, and now yeah, I'm gonna probably have to rerun my neural network.
Is it a kosher hot dog?
Oh dear, we're gonna be here all night.
It's not could you cut it, but would you cut it?
Would you cut it? Is a 3D printed gun a gun? All right. I am a big fan of the TensorFlow library. It's among the easiest way to get a neural network started. You do need a large data set, and there are numerous well-prepared data sets on the internet. I like going to the University of, the UCI data set. There we go.
Yeah,
DuckDuckGo, yeah. The breakfast of champions. There we go. The UCI data set has just thousands of data sets. That is great for learning machine learning. And then find a data set. This is where I found the poker data set. There are numerous data sets on here. If you're just starting out, learn the iris data set. It's the famous iris data set is the hello world of machine learning, because there's only 4 variables and 1 output category. You're trying to figure out if a plant is one of 3 different categories. It's a real simple place to get started. And then you build a neural network, and then you can solve this problem really easily. This problem has been studied ad infinitum. The data set itself is from 1936. So it's got historical, it's both a valuable data set, plus it's also historical. And that is an overview on how to get started with, well, mostly an overview of what neural networks are, and then how to get started with doing your actual neural network programming. It's come a long way since I was in grad school, where I wrote these things from scratch. I literally wrote a Java neural network from scratch in grad school, and it took me 2 weeks. Nowadays, I can just say, import TensorFlow as TF in a Python program, and 39 lines later, I have a TensorFlow application ready. Let's go check in on our model. I should have stopped this thing at 5,000, but let's see how we're doing on the accuracy.
55?
Yeah, we're at 55 accuracy. This thing is not improving like I thought it would, but it's still creeping up. It's just not going up the speed as that I would hope. I would have hoped that would have been up into the 60s by now. But everyone, thank you for your attention. Oh, yeah, question?
So once you got done training it, what would you do with it?
What would I do with it? I would start applying it in a real-world application, where I would take a poker, I would take 5 random cards, I would give those 5 cards to the model, and it would say that you have a straight. And so that's the real benefit of this particular application. All it does is determines the strength of a poker hand. But it does it. Well, counting cards is illegal. So I would have to. Counting cards is not illegal if you don't have any outside assistance. If you just do it in your head, then it's fine.
Although they'll still kick you out.
They'll still kick you out if they think you're doing it. And they have a right to do that. But anyway, thank you so much for your attention. Any other questions?
One of the slides that you had has the different types of machine learning.
Machine learning, yes.
Classification. Supervised.
Yeah, supervised, yes.
So
I just kind of briefly went over those, and well, in fact, I just kind of said there they are, and just went on to the next slide. Yeah.
just, I guess.
Where would
Yeah, so what do you call it? Neural networks would go under the supervised learning.
I think of networks as a version of supervised learning. Let's find out what Mr. Wikipedia has to say. It is a supervised learning. I'm always hesitant to say which algorithm is part of which category, because I can never remember all of them. But Wikipedia does have this under the supervised learning category, which you do have inputs and outputs, and you are supervising the entire process. You are.
You give it a test set and
a test set and a training set.
In order to.
Yep. All right. Any other questions or thoughts or concerns? Happy Veterans Day weekend, everyone. Thank you to all of our veterans. Have a good weekend.
All right.